Okay. So, sorry. Started the recording a little bit late. But the first thing that we can do to increase the speed at which a solid dissolves in a liquid is to agitate a solution. That means you can stir or shake your solution. You can stir and shake these things together. So stirring in some sugar into some water, for example, will increase the speed at which the sugar dissolves in the solvent, the water. The reason that that increases the speed of dissolution or dissolving is because we are increasing the rate of contact between the solute and the solvent, okay? Stirring will bring fresh solute in contact with fresh solvent, okay? If you're stirring them together, you're agitating that solution such that they are now in contact with one another. That is helping it to dissolve faster, okay? So that is why oftentimes if you are preparing some tea, you will stir it to help that dissolve. That increases the rate. The second thing you can do, the other thing you can do, is increase the surface area of your solute, okay? For example, if you have a whole bunch of your solute and you break that solute into smaller pieces, okay, you break that solute into smaller pieces, you can expose more of the solute to the solvent by breaking it into smaller pieces. There's going to be more collisions between the solute and the solvent if it's in smaller pieces. This is why if we were to, do an experiment in dissolving sugar into tea, if you had some granulated sugar, some little small pieces of sugar versus a cube of sugar, you would actually observe if you had 1 gram of granulated sugar and 1 gram of cubed sugar, you would observe the granulated sugar dissolve faster because of its smaller pieces. It's able to get into contact, get into more collisions with the solvent. Okay? Bless you. So increase the surface area to expose more of the two together, agitate to bring fresh solute in contact with fresh solvent, and the third thing we can do is increase temperature. If you increase the temperature, you will be adding, by definition of temperature, more kinetic energy to that system. If there's more kinetic energy, there's more movement. If there's more movement, there's more collisions between your solute and your solvent particles. So higher temperature, higher kinetic energy, more movement, faster dissolving. So all of those things can increase the speed, bless you, at which your solute, your solid solute, dissolves in a liquid solvent. Okay. The other thing we talk about when we're talking about factors affecting solubility is the amount of solubility. Okay. The amount of solubility. The amount of solubility is how much solute can dissolve in the solvent. So this is not having to do with the rate. This is the overall quantity of solute that can be dissolved in a solvent. Okay? You may be able to, make something dissolve faster by stirring it, but stirring something is not necessarily going to increase the amount of solute that can dissolve in a given amount of solvent, like water. Okay? One thing you can do to increase the amount of solute that can dissolve is you can, of course, add more solvent. If you add more solvent, there is now more solvent, there's more substance like water for a solute like salt or sugar, for example, to dissolve it. You increase the amount of water, you increase the amount of solvent, you can increase the amount of solute we can put in to that solvent. Okay? Adding more solvent is not going to increase the concentration, though. Just be mindful of that. Even if you add more solvent, you're not increasing the concentration of a substance, because now we're adding, your concentration is dependent on the amount of solute per unit of solvent. If you're adding more solvent, you have more solvent for that solute to spread out in. That's actually technically decreasing the concentration. Okay? Unless you continue to add more solute, then you can keep that concentration constant. But this is not a method by which we can increase concentration. The way that we can increase concentration is by altering the temperature. So temperature is both something we can alter to influence the speed at which something dissolves, as well as the amount of solute that we can shove into some amount of solvent. Altering the temperature, the way you alter the temperature to get more solubility, to get more amount of solubility, will depend on the substance that you are dealing with. The trend is different for solids and for gas solutes, okay? So we're going to look at solid solutes first. So we have something in the solid state, something like, a sugar crystal or some salt crystals. If we tried to get those to dissolve in water, if we increased the temperature here, we could increase the solubility, the amount of solubility. Okay? And this is actually what you can do for sweet tea. If you want to make your tea sweeter, you can heat up the tea, and by heating up the tea, you can actually get more sugar to dissolve in the tea solution. So for this reasoning right here, I want you to write that an increase in temperature will allow for an increase in the number of collisions, and there will be, therefore, more effective dissolving. Okay. So increasing the temperature will allow for more solid solutes to dissolve in a water solution. Yes, do you have a question? It can. So the question was, does it undissolve once it gets colder? Depends on how fast you cool that solution down. We'll talk about this a little bit later in the notes, but if you cool it down slow enough, it actually will stay dissolved, and so it'll stay super, super sweet. And so that's one of the ways that you can get really, really sweet iced tea. But if you cool it down very quick, or you do something to disrupt, what we call disrupt the solution, then you can actually knock out all that extra sugar that you have dissolved in it. And so we'll talk about the reasons for that later as well. Yeah. But yes, you can make your tea super, super sweet, and then if you cool it down slow enough, you can make it so that that sugar stays in that solution. Gas solutes are a little bit different though, okay? If you increase the temperature for a gas liquid solution, so gas solutes in water, the solubility actually decreases. And this is the reason why your soda will go flat on a hot day, or if you don't keep it in the fridge. So when you have a cold temperature, when things are cold, that actually increases the solubility of gases in water. And so the reason why soda is so bubbly when it is cold is because there is much more carbonation. There's much more CO2 still dissolved in your soda when it is cold. If your soda starts warming up, you open up your soda and you leave it out in the sun on a hot day, you'll notice after a while that your soda gets flat. And that's typically not very good. Most people don't like flat soda. So when it is cold, it's got more bubbles, more carbonation than when it is hot, okay? When you heat up something like a soda, which is a solution, it's a solution, it's got sugars in it, it also has gas like CO2 in it. When you increase the temperature of soda, what that does is that causes the molecules to spread out. That's what happens when something is heated up. The molecules spread out. Why this matters, though, is because for gas solutes, if the molecules start spreading out like that, if you start heating up something that has dissolved gases in it, like soda, when the molecules spread out, the gas molecules can actually escape from the solution. So heat up your soda, your gas molecules will escape. No more bubbly soda, no more carbonation, no more dissolved CO2, or very, very small amounts of dissolved CO2. So that is one thing, that's one of the factors that helps soda stay bubbly, is being cold. So that's why you typically want to, when you're going to drink a soda, most people put their soda in the fridge, get a nice cold soda out of the fridge. The other thing that affects the ability of gas solutes to dissolve in water is the pressure, okay? So I want you for this third blank right here. The third factor that affects the amount of solubility, how much solute we can dissolve in a solvent, is pressure. This mainly only affects the solubility of gases in liquids, such as CO2 in a soda. Okay? Gas solutes in water, such as CO2 in a soda, if you increase the pressure on that solution, you actually will increase the solubility amount. Okay? Soda has more carbonation when the can or the bottle is closed versus when it is open. Okay? The reason for that is because if you have a greater pressure on your solution of gas in whatever solvent, like water, you increase the pressure on that CO2 water solution, for example, and this is the same thing that happens for carbonated water as well, if anybody likes sparkling water. You increase the pressure on that gas solvent solution, you cause the molecules to become squeezed together. You're putting pressure, you're essentially pushing the molecules together. Squeezing the molecules together, putting pressure on that, keeps the gas molecules in the solution. So I'm going to write that gas molecules stay in solution. Gas molecules stay in solution. So, of course, many people are already aware of this phenomenon of, the pressure and the temperature. We've seen this example in our lives. We maybe just didn't know the scientific reasoning behind it. We just made these observations. I think the solid solutes in water is a very common observation that many of us have made. We know that if our tea is hot, we can dissolve more sugar into it, or, if you're trying to make sugar water, maybe you were trying to fill up a hummingbird feeder or something, you know that if you heat up that water, you can dissolve more sugar into it. Maybe not so common, we didn't maybe realize that for gas solutes in water, the colder the temperature, the more gas we can dissolve, such as in soda, and the more pressure on that solution, the more gas we can dissolve. So your way to remember these gas solutes, these temperature rules, and these pressure rules for gas solutes, I would definitely remember soda, okay? Soda is what I always think of when I'm trying to remember these relationships. If you remember that soda is most carbonated, it's most bubbly and most filled with CO2 when it is cold and closed, then that can help you remember that cold temperature and high pressure is going to increase the amount of gas we can push into a solution, essentially. So the closed bit is the high pressure bit, and the cold bit, of course, is the temperature bit. So soda is most carbonated, it is most bubbly and full of CO2 when it is cold and closed. Okay. What questions do we have about these amount of solubility versus rate of solubility? Like I said, I want you to be familiar with these pieces. What can increase the rate or the speed at which we dissolve? What can increase the amount of a solute we can dissolve? You don't need to worry about pressure with solids. We don't really talk about pressures, how that affects the solubility of solids. It really only affects gases. But be familiar with those three things for each concept up there. The last thing I'm going to have us go over before we flip to the next page and start, kind of talking a little bit more about, more explaining the question about, what happens when we cool down something that has a whole lot of sugar in it, for example, is the saturation levels. I want to define 3 words that pertain to saturation levels. The first word I want you to write in here is saturated. Okay? You're going to write saturated. A saturated solution contains the maximum amount of dissolved solute for a given amount of solvent at a specific temperature and pressure. Okay? Bless you. In other words, we have dissolved everything that a solubility chart says we can. So we're going to look at some solubility charts a little bit later today. But right now you just need to know saturated, the maximum amount that we can dissolve in something. We say something is saturated when it's basically full of solute. We can't add any more solute in, it won't dissolve. We also have two other terms. We can modify this saturated word so that it is unsaturated or supersaturated. So unsaturated means that you have a solution that contains less than the maximum amount of dissolved solute. This means that we can still dissolve more if we want to. There's still room in the solution to dissolve more solute. If we put more solute into an unsaturated solution, then it will dissolve. If we put more solute into a solution of unknown concentration and our solute dissolves, we know that we had an unsaturated solution. The other term is supersaturated. So super means like a lot or much. So a supersaturated solution is one that contains more dissolved solute than a saturated solution at the same temperature. So we have essentially forced more solute to dissolve in a solution to make a supersaturated solution. And this is what I was talking about earlier when I was trying to answer your question. Yes, you can cause a solution to take in more sugar essentially than it probably should at that temperature. But in order to do that, you have to do something like heat it up. Okay? We force more solute to get dissolved, we heat up the substance, and then we cool it down very, very slowly, and that is how you get sweet tea. Typically, if you're making, traditional southern sweet tea, you'll heat it up, you'll dissolve a whole bunch of sugar in it, and then you'll cool it down very slowly, and that's how you get it so sweet, is we essentially have a supersaturated solution on our hands with a ton of sugar dissolved in it. So those are our three terms. Is anybody still using what I have up on the board? Cool. Then let's talk about how we can make a supersaturated solution, which is how you can make sweet tea, for example. So we have a whole little paragraph up here that talks about this. Again, a supersaturated solution is that solution that contains more solute than normal for that temperature. Because that solution contains more solute than normal, it is unstable. Okay? It is in this kind of unstable state. The unstable state can be disrupted if we add more solute into the solvent or we, do something else to disrupt this. So when we disrupt a supersaturated solution, we can actually cause it to go back to a saturated state. We can knock out all of the extra solute that was dissolved in that supersaturated solution. Okay? So for example, you can have a case where you have your sweet tea, and if you add more sugar to your sweet tea, adding that more sugar can actually disrupt the solution and make it less sweet, because now we've knocked out solute from the solution and there is less sugar dissolved. It's just hanging out on the bottom, which is kind of gross if you get to the end of the cup and take a big drink. After the disruption occurs, after we've knocked out all that extra solute and it's just hanging out on the bottom, we consider the solution to be saturated again. So we're going to look at this example down here. We're going to do some labeling so we can illustrate essentially what happens when we make a supersaturated solution and what happens when you disrupt a supersaturated solution, aka how your sweet tea becomes less sweet if you add more sugar. So here, this first picture is our room temperature saturated solution. So this being saturated at this point, I want y'all to write this is holding the max amount of solute that it should at room conditions. Okay? Holding the max amount of solute that it should at room conditions. So the spacing of the solute within the solvent is roughly this in its saturated state. You can make a supersaturated solution by adding in, you can add in some more solute. So I'm going to draw my little circle here and draw an arrow to indicate I'm adding in more solute. And then I heat this up. I'm going to write heating up so you can dissolve more. you heat this up so you dissolve more, and then you add in some more solute, at this point it's saturated because we raised the temperature. If you increase the temperature of most solutions for solutions that have solid solutes in them, that will allow for more to be dissolved. And then if we cool this down very slowly, so I'm going to write cooling down slowly. If we cool this down slowly, such that now it's back at room temperature, so we were at room temperature over here, now we're back at room temperature again. We now have ourselves a super saturated solution, okay? This solution is holding more than the max amount of solute. Bless you. The only reason this is holding more than the max amount of solute is because we heated it up, added more solute, and then cooled it down very, very slowly. That is how you make a supersaturated solution. And like I said, you can disrupt this supersaturated solution by doing something like adding more solute to your supersaturated solution. Adding more solute to a supersaturated solution is a disruption. And what happens then, if you add this solute like so, you actually cause some of the extra, all of that extra solute to fall out or precipitate out of the solution. And so what you see is that it will look like a layer. If you did this to some iced tea, for example, it would look like there was a layer of sugar along the bottom of your glass. Because we've knocked out all that extra sugar. Normally sugar dissolved in water, you can't see the sugar particles. But if you knock out that extra sugar, it's going to, become those little particles again, those little granules. And so the extra solute precipitates out of the solution. I'm going to put a little more of a space there. The extra solute precipitated out of the solution, and the solution is going to return to its saturated state. So I'm going to draw the particles in the same spacing that we had originally over here. Okay? So that's roughly what we looked like, right? About that concentration. No longer supersaturated. The solution returns to the saturated state. Again, this layer here does not represent dissolved particles. This is the precipitated solute. This is the not dissolved pieces, and these are all the dissolved pieces suspended in the water. Okay, so I want to show you all a quick video of this actually happening so you can actually see like the physical representation. So I'm going to pause my video and pull that up. So what we have down here, our next example, we have 4 different solutions of unknown concentration with aka, varying amounts of NaCl. And then we add 30 grams of sodium chloride to each one of these unknown solutions. We stir for 5 minutes, and then we observe the amount of solute at the bottom after 5 minutes. So again, these are our initial solutions. These are our initial solutions of unknown concentration. To each of these 4 unknown solutions, we are going to add 30 grams of sodium chloride, and then we're observing how much sodium chloride we see at the bottom of the container after stirring for 5 minutes. And in doing that, we can figure out if the original solution is saturated, unsaturated, or supersaturated. So I'm going to do this first one with you, and then I want to challenge y'all to do the next three. For this first one, this unknown solution 1, we don't know what its concentration is, but we do know that when we add 30 grams of sodium chloride, after we stir for 5 minutes, there's 0 grams of sodium chloride left at the bottom. What does that mean? What happened to all 30 grams of the sodium chloride, y'all? Dissolved, right? So this all dissolves. I'm going to write, so all dissolves. Okay? If all of that dissolved, what was our original solution? What must our original solution have been? What did we say? Unsaturated, yeah. Unsaturated. Unsaturated. There was still room for more to be dissolved. If any amount that you add dissolves, your original solution was unsaturated because there was still room for more solute to be dissolved. So your challenge now is to figure out if solution 2, 3, and 4 were saturated, unsaturated, or supersaturated based on what we see after 5 minutes. So work on those. You can work with your table, and then we will go over those here shortly. So we add 30 grams of sodium chloride to our solution 2, and after stirring for 5 minutes, we notice there are 45 grams of sodium chloride at the bottom. So what do y'all think the original solution was? It was indeed supersaturated. How could you tell? There was more at the bottom than when we started, exactly. There was more at the bottom than when we started. How much more at the bottom was there? 15 grams. 15 grams must have precipitated out of our solution, right? So we know that this was supersaturated. We know we disrupted it, and we knocked out 15 grams extra. Okay? What about solution 3? Solution 3, we dissolved 30 grams of sodium chloride, and after stirring for 5 minutes, there's 30 grams at the bottom. Saturated. Why do you say that? What does saturated mean? Maximum amount, right? Maximum amount. So we already had the maximum amount in the solution. We couldn't shove any more in, basically. So the 30 grams just fell to the bottom. Very good, y'all. Any questions so far? Okay. Then our last solution, we added 30 grams of sodium chloride, and there were 10 grams left over at the bottom. What was our original solution? Unsaturated. Why do you say that? How much dissolved, y'all? 20 grams. So 20 grams must have dissolved. If 20 grams dissolved, there was still room in that solution to dissolve more. So our original solution must have been unsaturated. After those 20 grams dissolve, what is the solution now? After all 20, saturated. Yeah, very good. Would have been saturated. Okay? Any questions there before we go to our next page? Awesome. Let's go ahead and flip to page 14 then. We can talk about solubility curves. So here are solubility curves. This one is showing the solubility of solid ionic salts, and this one is showing the solubility of gases, okay? What you will notice about solubility curves is typically solubility. I want you to notice this y-axis here. We have an x-axis of temperature, okay? So as we go more right, we're increasing our temperature. And then your y-axis is your solubility. So here we have grams of solute per 100 grams of water. Typically, that is what you are going to see. You're going to see your y-axis talking about solubility in terms of grams of your solute per 100 grams of H2O. That will be important here in a little bit. Okay? So per 100 grams of H2O. grams of solute dissolved per 100 grams of H2O. Sometimes this is different, but for most charts, it is per 100 grams of water. So make sure you are aware of what your chart shows, because we're going to have to start potentially making some adjustments, setting up some proportions if we have something that does not quite match up with our 100 grams of water in our question. And I want you to notice the general trend for the solubility of solids with increasing temperature and the general trend for the solubility of gases with increasing temperature, okay? I'm going to use this yellow marker to show when solubility is increasing as temperature goes up, and I'm going to use this green marker to show when solubility is decreasing as temperature goes up, okay? So I notice I've got a positive slope for a lot of these guys here. Okay. See all those? And I've got a negative slope for, NH3, this ammonia here, and then this cesium sulfate. Okay. Look at my gases. So what do we notice in general about the solubility of solids with increasing temperature? It goes up, right? It's increasing. Yes, so as my temperature goes up, I'm just going to use T for temperature, my solubility of solids in general, there's some exceptions obviously, but in general, the solubility of our solids increases. What about for our gases? What happens to our gases as our temperature increases? Decreases. Yeah, our solubility of our gases decreases. Solubility of gases decrease. So that's exactly what we talked about on the first page of our notes today. We talked about that trend. If we increase the temperature with a solid solute, typically the pattern is that the solubility increases, the amount of solubility increases, and if we increase the temperature for gases, the amount of solubility decreases. And we can use these solubility curves for a lot of different purposes, okay? Some of those we're going to practice with on the next page. I wanted to relate to you some things about these solubility curves and our terminology, saturated, supersaturated, and unsaturated. I want you to be aware that any amount of solute that is below the line would indicate an unsaturated solution, okay? So unsaturated solution would be something below a line. For example, if we were looking at a substance like potassium nitrate, KNO3 here, okay? If I'm looking at 50 degrees Celsius, KNO3 here, okay? At 50 degrees Celsius, I can dissolve a maximum of 80 grams of potassium nitrate per 100 grams of water that I have. So if I'm at anything below 80 grams, if I have 70 grams, for example, or 60 grams of potassium nitrate at 50 degrees Celsius in 100 grams of water would be considered an unsaturated solution because it is below the line, okay? I can still dissolve another 20 grams if I wanted to, so therefore my solution is unsaturated, below the line. If we are above the line, an amount of solute above the line that has dissolved, if everything has dissolved, we would consider that to be a supersaturated solution. For example, let's look at potassium nitrate again. If I had 100 grams of potassium nitrate fully dissolved at 50 degrees Celsius in 100 grams of water, I would consider that to be a supersaturated solution if all 100 grams was fully dissolved. If we have an amount before or above the line like this, 100 grams above the line, but not all of it is dissolved, okay, that means that the solution is saturated and the extra grams of solute have precipitated or settled to the bottom. So if I have a saturated solution of potassium nitrate, for example, at 50 degrees Celsius, and I say that there's 100 grams in there, but the solution is only saturated, that means that 20 grams are just hanging out at the bottom. Okay? Where do you think a saturated solution would fall in relation to the line, y'all? Yeah. On the line. It would be on the line. So, saturated solution is on the line. And down here we talk a little bit about proportions and such. So we are going to do that. I'm going to do an example with you on the next page with these. But we're going to keep this in mind as we look at our examples on the following page. Is anyone still using what I have on the board? Cool. Then go ahead and flip to page 15. We're going to do some examples with this solubility curve. So again, I want you to notice that we have this y-axis over here per 100 grams of water. That will be something we want to keep in mind as we do these problems. Okay? So for the first example, we are told to figure out, to determine if the solutions are saturated, unsaturated, or supersaturated. For letter A, we are told we have 40 grams of potassium chloride. 40 grams of potassium chloride dissolved in 100 grams of water, which matches our axis over here, at 80 degrees Celsius. So what I like to do is I like to, highlight what I'm looking at so I don't get all my lines confused, because as you can see, you have a ton of different lines here. Okay? So that is our potassium chloride. And how we could figure out this is we could just line up our 40 grams and our 80 degrees Celsius. So we know 80 degrees Celsius is right here, and we have 40 grams right here. Okay? So 40, 80 degrees Celsius. Where is that spot in comparison to the KCl line? It is below. So are we saturated, unsaturated, or supersaturated? Unsaturated. If we have 40 grams of this, we can still dissolve another 10 before we reach saturated, right? So we are unsaturated at this point. This solution is saturated at 80 degrees Celsius with 50 grams, not 40. What about KNO3, okay? KNO3. We've got 120 grams. There's my 120 grams. Completely dissolved in water at 60 degrees Celsius. Where is this spot in relation to the KNO3 line, y'all? It is. It's above. It is above. So 120 completely dissolved in 100 grams of water. What would that make that solution? Super saturated. Very good. Okay. And then letter C, let's do a different color. Sodium nitrate here. Letter C. I can even label these if I want to. This is A. This was B. Letter C, 80 grams of sodium nitrate completely dissolved in 100 grams of water, still matches over here, at 10 degrees Celsius. Okay, 10 degrees Celsius, 80 grams, right here. This is letter C. Where is that in relation to the NaNO3 line? It is on the line. If something is on the line, what do we consider it to be? Saturated. Very good. This is saturated. Okay? What questions do we have about those first three? Okay. The next example asks, which of the salts shown on the graph is the least soluble in water at 10 degrees Celsius? So, 10 degrees Celsius, right? There's 10 degrees Celsius. What you're going to want to do for a problem like this is you're going to want to follow 10 degrees Celsius up and see which line you hit first, okay? Which line do we hit first, y'all? KClO3, right? KClO3, okay? At 10 degrees Celsius, the maximum amount of KClO3 that can be dissolved such that it is a saturated solution is going to be like 6 grams, okay? Nothing else has fewer grams dissolved in it at that point in the solubility curve to give us a saturated solution, okay? So the least soluble one is going to be our KClO3, okay? We can dissolve the fewest grams of KClO3, potassium chlorate, in that potassium chlorate solution at 10 degrees Celsius. These next two you should be able to do if you are able to interpret the slope of something. Whether or not a slope is steep or whether or not a slope is not steep is going to help you figure out the answers to these two questions. So I want you to try and figure out which of the salts shown has the greatest increase in solubility, looking at a temperature increase from 30 to 60 degrees. I also want you to try and figure out which of the salts has solubility affected the least by a change in temperature. Okay, so try and figure those out, and then we will go over that. Look at the slope. That's my hint to you. Look at how steep the lines are. Okay, let's take a look at these now. You've had some time to think about them. So for this first one, the greatest increase in solubility from 30 to 60 degrees. Are we looking for a steep slope or a not so steep slope here? A steep slope, right? Greatest increase, looking for a steep slope. Which of these curves has the steepest slope between 30 and 60, y'all? Okay, NO3, very good. Potassium nitrate. What about this next question? The solubility affected the least by a change in temperature. So what are we looking for slope-wise here? A fairly straight, or how would you say straight? Like vertically straight or horizontally straight? Horizontally straight, right? So the smallest slope in terms of like absolute value, not necessarily the fact that it's negative, okay? So for our smallest slope here, which one has the solubility affected the least by the change in temperature? NaCl, yeah, this little guy that was kind of trying to hide. It almost looks like a line straight there, but that is NaCl. Okay. Any questions there? Yeah, absolute value. Okay, smallest slope. Okay, so our next couple of examples are going to deal with, again, still reading this chart. The first example asks us, how many grams of potassium nitrate will it take to saturate 100 grams of water at 50 degrees Celsius? Okay, so this, how you could figure this out, y'all, is you want to go to your chart at 50 degrees Celsius. We know that this is a per 100 grams of water chart. We want to look at 50 degrees Celsius and potassium nitrate here, okay? KNO3, which was we already looked at this one. This was our yellow one, potassium nitrate. So we want to know, at 50 degrees Celsius, how much of this can we saturate? How much potassium nitrate will it take to saturate that many grams? And so if we look at our 50 degrees Celsius, look at where we cross the line there, we get 80. Okay? 80 grams of KNO3 will saturate our 100 grams of H2O. So our example is 80 grams of KNO3. Okay? So that is just reading the chart as we have been doing. You basically go and match those up there. The next example is also asking about potassium nitrate. But here it asks us how many grams of this substance would it take to saturate 300 grams of water at 50 degrees Celsius. So this is a case, bless you, where we would have to set up a proportion, okay? So up at the top of your page, I want you to write this little note, now that we are dealing with something that is not 100 grams of water. Please make sure anytime you are doing one of these problems, up until this point it has not been a problem because they've all been 100 grams, check your water, check the mass of your water. If it's not 100 grams, you need a proportion. Okay? If it's not 100 grams, you need a proportion. So up until this point, we've not needed a proportion, bless you. But if you have an amount of water that is not 100 grams, you will need a proportion. So that is why I kind of wrote the answer to that first example down there as a fraction, so we can set that up. Is anyone still using what I have up on the board up top here? Okay. Then down here, how many grams of this will we need to saturate 300 grams of water? Okay, we know at 50 degrees Celsius, we just figured that out, 80 grams of potassium nitrate will saturate 100 grams of water. And so we can set up a proportion to figure out how many grams of potassium nitrate would saturate 300 grams of water. It's just multiplying 80 times 3. Okay? It's 300 times 80 divided by 100. So if you do that in your calculator, go ahead and calculate that. If you can't do it in your head, if you can do it in your head, then awesome. What value do we get there? 240. Yes, sir. Yes, I need you to show work on your test. Yeah. 240. So you get 240 grams of this. Very good, y'all. Any questions about that one? Okay. On this final example, we're still dealing with the same substance. We're back to our 100 grams of water, though. Here, we're told that 100 grams of water containing a saturated potassium nitrate solution is quickly cooled to 10 degrees Celsius. We want to know how many grams of potassium nitrate will precipitate out of the solution. So how many grams will fall out of the solution if we quickly cool this from 50 to 10? So what I would do is I would write out, of course at 50 degrees Celsius, 80 grams of potassium nitrate will saturate the solution. Okay? Saturated solution of potassium nitrate at 50 degrees Celsius contains 80 grams of that potassium nitrate. What we also need to know is how many grams of potassium nitrate are contained within a saturated solution at 10 degrees Celsius, because that's all we're going to be able to hold at 10 degrees Celsius. So if we go back up to our chart, at our 10 degrees Celsius, we go up, we find the potassium nitrate one. Well, there we are, right here. I'm going to estimate that at about 22 or so. Does that sound acceptable to y'all? Okay. So we know there's, roughly 22 grams or so of potassium nitrate in a saturated solution of that substance at 10 degrees Celsius. So if we quickly cool it down, what's going to happen to anything above 22 grams, y'all? We had 80 grams in the solution, but at 10 degrees Celsius, we can only hold 22. What's going to happen to the other? It's going to precipitate out, right? It's going to fall out. So extra will precipitate out. That's what our problem was asking us about. Okay? So you just find the difference between these two. Okay? 58 grams will precipitate out. 58 grams will fall out of the solution. What questions do y'all have there? Okay. The last page, I am going to challenge you to do that yourself, but I will give you the answers to each of the questions. I'll also post my key with the work later on Canvas so y'all can look at that if you get stuck on one. So this first example, I'm going to give you the answer. The answer to this first one is going to be about 21 degrees Celsius, depending on how you estimate that. You may estimate it a little bit higher or lower. The answer to this second one is saying, would the solution be saturated or unsaturated? It's going to be saturated. The second half of this answer is there's 8 grams at the bottom. Yes. The answer to this third one, 20 grams. To the fourth one, 116 grams. And the last one, the answer is 50 degrees Celsius. Okay? So those are your answers. So you can check your work when you're done. If you get stuck, you can, of course, ask me in the remaining time we have today, or I will also, if you don't get to one of them today in class, I'll have the work posted on Canvas as well. Does anybody have any questions I can answer at this time, though, before I let you go to work on these? Okay, you're going to go ahead and get started on working on those.